Parametric substitution for implicit equations. Hello everyone. To begin today's lesson, let's first recall that in our previous sections, we have already learned the process of finding derivatives for functions that are provided in parametric form. However, as we move forward, we often encounter implicit equations. These are equations where the variables x and y are mixed together in a complex manner, making it difficult to express one variable explicitly in terms of the other. While it is possible to differentiate these equations directly using implicit differentiation, you will find that the algebra involved can become quite tedious and cumbersome. To overcome this, we can introduce a third variable known as a parameter. By doing this, we can simplify the entire problem through a method called parametric substitution. In the upcoming slides, we will dive deeper into how to implement this substitution and the specific scenarios where it is most useful. Understanding parametric substitution. Now that we have established why implicit equations can be challenging to differentiate, let's look at the actual mechanism of parametric substitution. First, the core idea is to replace our original variables, x and y, with expressions that are defined in terms of a new third variable. In mathematics, we typically use the letter t or the Greek letter theta for this purpose. By doing this, we transform a single, complex implicit equation, where x and y are tangled together, into two separate and much simpler equations. Specifically, we express x as a function of t, and y as a function of t. This effectively decouples the variables, making them easier to handle individually. Once we have these two simpler functions, we can find the slope of the curve using the standard parametric differentiation formula. This formula states that the derivative of y with respect to x is equal to the derivative of y with respect to t, divided by the derivative of x with respect to t. In the next slide, I will explain how to identify which specific substitutions to use based on the geometric form of the equation you are facing. When to use parametric substitution. Now that we have established the general concept of parametric substitution and the formula for finding the derivative, you might be wondering when exactly this method is the best approach to take. The key is to observe the structure of the equation. This technique is particularly useful when the implicit equation resembles a known geometric identity. First, let's consider circular or elliptical forms. If you encounter an equation such as x squared plus y squared equals r squared, or a more general elliptical form where x squared over a squared plus y squared over b squared equals 1, you should utilize trigonometric substitutions. Specifically, we use sine theta and cosine theta, as these functions naturally satisfy the fundamental trigonometric identity. Similarly, if you are dealing with hyperbolic forms, where you see a difference of squares rather than a sum, such as x squared minus y squared equals a squared, you should use substitutions involving secant theta and tangent theta. By recognizing these patterns, you can simplify a complex implicit relationship into two manageable parametric equations. In the next slide, I will guide you through the exact step-by-step process to execute this substitution and find the derivative. Step-by-step process for parametric substitution. Now that we have discussed when it is most appropriate to use parametric substitution, let us walk through the systematic, step-by-step process to execute this method. First, you must identify the pattern. Look closely at your implicit equation and determine which trigonometric or algebraic identity it resembles. As we saw in the previous slide, recognizing whether it is a circular, elliptical, or hyperbolic form is key to choosing the right path. Second, choose the parameter. Once you have identified the pattern, select an appropriate parameter, most commonly the Greek letter theta, and define both x and y as expressions in terms of this parameter. Third, differentiate x. You will need to find the derivative of x with respect to theta. Fourth, differentiate y similarly. Find the derivative of y with respect to theta. Fifth, apply the formula. To find the final derivative of y with respect to x, simply divide the derivative of y with respect to theta by the derivative of x with respect to theta. Finally, you may perform back substitution. This step is optional and depends on the requirements of the problem. If you need your final answer in terms of the original variables rather than the parameter, you will substitute the parameter back using your initial definitions. To see how these 6 steps work in a practical scenario, let us move on to the next slide and look at an illustrative example involving planetary orbits. Illustrative example. Now that we have established the theoretical step-by-step process, let us apply it to a practical illustrative example. To give you some real-world context, this method is highly relevant in astronomy, as planetary orbits are elliptical and are typically represented by implicit equations. Our specific problem is to find the derivative, di by dx, for the equation x squared over a squared plus y squared over b squared equals 1. Following the first step of our process, we must choose an appropriate parameter. As we mentioned in the previous slide regarding elliptical forms, we will substitute x with a times cosine theta and y with b times sine theta. Next, we move to step 2 and differentiate x with respect to theta. The derivative of a cosine theta is negative a sine theta. In step 3, we do the same for y. Differentiating b sine theta with respect to theta gives us b cosine theta. Now, we apply the parametric differentiation formula we introduced earlier. By dividing the derivative of y by the derivative of x, we get b cosine theta divided by negative a sine theta. This simplifies to negative b over a times cotangent theta. Finally, in step 5, we often need to express the result in terms of the original variables, x and y, rather than the parameter theta. Since cotangent theta is the ratio of cosine theta over sine theta, we can substitute our original definitions to see that cotangent theta equals x over divided by y over b, which simplifies to x times b over y times a. When we substitute this back into our derivative expression, we arrive at the final result. Di by dx equals negative b squared x over a squared y. While this example demonstrates the efficiency of the method, it is easy to make small errors during these steps. Therefore, let us move to the next slide to discuss common mistakes to avoid. Common mistakes to avoid. Now that we have walked through the step-by-step process and seen a practical example with an ellipse, it is important to discuss some common pitfalls. Let's look at the common mistakes to avoid to ensure your calculations are accurate. First, be mindful of incorrect substitutions. When you define x as a function of t and y as a function of t, you must ensure that these expressions actually satisfy the original implicit equation. If your chosen substitutions do not plug back into the original equation to create a true statement, your entire derivation will be flawed from the start. Second, watch out for sign errors. This is a very frequent mistake in calculus. Specifically, always remember that the derivative of cosine theta with respect to theta is negative sine theta. Forgetting that negative sign is a simple error, but it will lead to an incorrect final answer. Third, consider the possibility of division by 0. As we saw in our formula, the derivative of y with respect to x is the quotient of the derivative of y with respect to the parameter divided by the derivative of x with respect to the parameter. Therefore, if the derivative of x with respect to theta equals 0, the overall derivative is undefined. Geometrically, this often corresponds to points where the curve has a vertical tangent. Finally, avoid mixing your variables. To maintain consistency, you must differentiate both x and y with respect to the same parameter. You cannot differentiate x with respect to one variable and y with respect to another and expect the parametric formula to work. By keeping these points in mind, you can avoid the most frequent errors. Now, let us move to the final slide to summarize the key takeaways of this lesson. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of this method. First, remember that parametric substitution is a powerful tool that allows us to take a complex implicit equation, where x and y are tangled together, and convert it into two simpler, separate functions of a third variable, which we call the parameter. As we discussed in the earlier slides, this approach is most effective when the implicit equation matches a known geometric identity. A prime example of this is the trigonometric identity, where sine squared theta plus cosine squared theta equals 1, which is why this method is so efficient for circular and elliptical forms. Regarding the calculation, the core formula we used throughout the process is that the derivative of y with respect to x is equal to the derivative of y with respect to t, divided by the derivative of x with respect to t. Finally, keep in mind that your final answer can be presented in two ways. You can leave the result in terms of the parameter, or, as we demonstrated in our illustrative example, you can perform a back substitution to express the derivative in terms of the original x and y variables.